Hi everyone. So our group would like to present the final project. So start with the introduction of ourselves. With me, Soravit Satechaichan.
My name is Sippakorn Vikornvongvanich.
And my name is Phakhawanon Pinsiri.
Okay, so let's start with the short introduction of the project. So the core concept is to implement an integer division algorithm, which find the quotient of Q and remainder R for unsigned input A and B. So we start by trying the algorithm using the repeated subtraction where R is repeatedly reduced by B while Q is increasing. The initial approach had two major flaws. The first one is it cannot handle the division by zero when b equal to zero. And the second one is it correctly handle the case where r equal to b. So we create an correct algorithm that fix both cases. So it check for b equal to zero first, and we also modify the loop condition of r minus b more than or equal to zero to handle b r equal to b correctly. For the design specification, we have both input and output, and the variable are addressed as follow in the table. So for example, A in mean the signal of dividend, B in mean the signal of divisor, and so on. Next.
Okay, so this is the first cut of the ASM chart. The state A is the idle, the state B is error, state C is running, and state D is finished. And there's like multi and more output.
For the data path circuit, the design consists of six main component types. The first one is four n-bit register for B, C, R, and D, and another four n-bit tri-state buffer, one subtractor, one comparator, and one counter for Q, and one controller unit. These components form our data path circuit as follows.
And this is the final ASM chart. It is a more detailed version of the first cut ASM chart. This is also the MDS diagram of the final ASM chart. And yeah, as you can see in the screen. And I will leave it to Phakhawanon to talk about the VHDL and test bench.
Okay, so we have done the design part. Now we go into VHDL code and implementation result. So we code the VHDL code like this. Like we have tri-state buffer, subtractor, register, which is rec, counter, controller, which is the finite state machine, and comparator. Then we connect all of these components together into a single integer divider. So as you can see here, we have all the system input and output, and then the signal, both the control and the connection between the components, and we declare each component here and set it like register B, register R, and so on. And for the RTL viewer for this code, as we can see here, it has the exact same connection as the data path circuit, but it's a little messy around here, so but I can ensure you that it's the same data path circuit that we have drawn earlier. And now for the result, uh, we use Cyclone V, Cyclone 5, and it utilized like less than 1% of our resource. It utilized 37 pin though, which is 14% because we implemented by like 8-bit integer divider, so it has a lot more pin. Yeah, as you can see here, the maximum fan out is the clock input, like the total connect to the number of the flip-flop that we have, which is 48. And for the fmax summary, which is for the frequency analysis, the maximum frequency that we can use is 180.11 megahertz, which translates to 5.288 nanosecond. So in our test bench, we select to use the clock of 10 nanosecond clock period. The code for test bench is here. We have 8 test cases which utilize all the paths in the final SM chart that we have drawn earlier. It covers the division by zero, like A is greater than B, A is equal to B, or A is less than B. We run this test bench and this is the simulation result. As you can see here, first we try to set the F reset to 1, which is the fourth reset of the integer divider. And then we try to input A equal to 37 and B equal to 3. And we go start. Then for the finished signal, it's the same thing here. Q is equal to 12 and R, the remainder is equal to 1, which is what we expected. The second test case, 61 divided by 11. Finished signal here. So the output is 5 and 6 for Q and R respectively. And third, we try division by 0. It's when you hit start, it gets stuck to this error signal. So this is what we expected. Now, for the fourth case, we try dividing 255 by 1. So this is the maximum time that it can take for the integer divider to perform. So as you can see here, the integer divider following the algorithm tries to increment its subtraction by 1. So as you can see, it takes a very long time by following the algorithm, and it gives the correct output, which is Q equal to 255 and I equal to 0. Then the other test cases as well. We try A less than B for this fifth test case. It gives correctly Q equal to 0 and I equal to 7. And we try A equal to B, 5 divided by 5. Obviously, it's 1 and 0. And also we test the case where A equals to 0. So 0 divided by 3 still gives 0 and R 0. Then 0 divided by 1 is still 0 and 0 for the output. So this is the test bench that we have implemented and it passes all the tests that we have given them.
Thank
Thank
you.
Thank you.
you.